Hello, Math 7 students. So today, this will be our last video of the year. So I'm jumping forward a little bit in terms of the curriculum. We're in topic 7, but I'm skipping a few things that are less important. We're going to move on to some real important things for probability and compound probability that you're going to want to know going forward. So just kind of break down what do we want to try to do is we're going to start with some probability trees. And so probability trees, you'll see it in the first problem. But we're basically looking at a way to break down some more complex probabilities and to kind of use that to build this concept of compound probabilities that will allow you to calculate probability quite a bit quicker using a multiplication property. And then finally, we're going to look at how to do some experimental probability to estimate some probabilities of some more complex situations. So that'll kind of round off our year. So let's start with the first problem. We're going to look at just a coin flip problem. So we're going to start with just a general coin, and you can actually view this as we're taking one coin, flipping it 3 times in a row, or we're flipping 3 coins at once and looking at all of them. But essentially the question is, what's the probability of flipping a coin and landing on heads 3 times in a row? So you're just flipping a coin 3 times, and you're going to see what's the probability of getting this outcome right here 3 times in a row. So like a heads plus a heads plus a heads. So we're going to break this down with our probability tree. So we'll start with just what's the probability of flipping once and getting heads. That's our first outcome. We got to get heads on the first time or we've already failed. So this one we can break down pretty easily. There's 2 possible outcomes. I can roll a heads or I can roll a tails, and they're both the same. They both take up the same kind of rotation on the coin. So really, there's 2 outcomes, and each outcome 1 and 2 are equally probable. So again, probability of getting it on the first flip is 1 and 2. And now you can see, well, flip number 2, we got to kind of keep track of some outcomes. So we can think of, if I were to flip this, I could flip a heads first, and on the second, I could also flip heads after flipping heads once. And I could also flip tails. So I've got, if I flip twice, I can do heads, heads, I can do heads, tails. And of course, I have to account for what happens if I flip tails again. So we'll extend this probability tree down. So we're just tracking all our outcomes. So I could go tails, heads, and I could also go tails, tails. So we count all our outcomes. I could go heads, 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 tails, tails, heads, or tails, tails. So I've got 4 outcomes. And if I were to look at just the outcome of flipping heads twice, well, it's really just this path right here. So 1 out of the 4 pathways leads to the outcome I want, 2 consecutive heads. So I've satisfied it for flip 1, flip 2. Now I got to do flip number 3, and we'll start looking at the patterns. So I could, of course, I get 2 branches here because I could go heads, 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 and I could also go heads, heads, tails. So heads, 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 tails. Let's keep tracking them. I could go heads, tails, heads, and heads, tails, tails. That's another possibility, and I'm just going to go ahead and move this over, give us a tiny bit more room. There we go. So I could go tails, heads, heads, and tails, heads, tails. So let's track that outcome. And this will kind of inform what we're going to do next. Because we have an easier way to break this down, but I just wanted to see the pattern first. And we also got to get tails, tails, heads, and tails, tails, tails. So you can see if I flip a coin 3 times, there are 1, 2, 3, 4, 5, 6, 7, 8 branching paths for 8 total outcomes. Or we could say one of the outcomes is heads, 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 tails, so on. We could count them all out. And again, so the probability of just getting the heads, 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 well, that's only this branch here. It's 1 out of the 8 branches. And now we can kind of start to see the pattern. So if I look at this, my outcomes each time, well, they doubled. So you could kind of use this as a predictive way to find, well, what if I were to do 4 heads in a row? And I said flip 4 times, how many of our heads? Well, the next one, we're just multiplying it by 2 each time, so 8 times 2, we get 16. So the probability would be a 1 in 16, and you can even do this with the probability. So here, we had double the outcomes to worry about, so that's like multiplying your probability by 1/2. 1/2 times 1/2 is a quarter, times 1/2 again, you get an eighth, times 1/2, again, you get 1/16. And you could see, you could easily extend this out and say, well, what about 8 times? And you could just multiply it by a half 4 more times. So you could easily calculate that probability without even doing any of these branches whatsoever. But you can see each time our possibilities double, so our probability halves. Then you can see, well, if this is something, if it was like a 3-headed coin, if that were possible, you could multiply this by 3 each time. So let's just take a look at applying this really quick, where we don't even have to make a probability tree at all. So let's apply this property. So I'm essentially going to formalize this really quick, where if I have 2 outcomes, let's say I have the probability of outcome 1 and outcome 2 happening, we can just multiply those probabilities together. And so let's apply it to this problem here. Again, if you want outcome 1 and outcome 2, just multiply those 2 probabilities together. Let's take a look at an example where I'm trying to land on tails and roll a 4. And I could branch this out and I could say, well, on my dice, I have 1, 2, 3, 4, 5, 6, and then I could do like my branches, heads, tails. I won't do all of these, but just to start where you can see, well, this will get kind of messy really quick. Or if I had to deal with another, let's say we had like another dice here, it would get quite annoying. So let's use that compound probability property instead. So I'm trying to get a tails and a 4. So outcome 1, outcome 2. Well, really all I need to do to get the probability of tails and right afterwards roll a 4 is I would just need the probability of rolling a tails, and then I could multiply it by the probability of rolling a 4. So we would just need to find out what's the probability of tails, what's the probability of 4. So we're pretty good already at doing both of these probabilities, where we know that tails is just one of 2 outcomes, so probability of tails, that's 1 in 2, 1 favorable out of 2 possible. And the probability of rolling a 4 on a dice, where there are 6 equal sides and they're all equally probable. So we have 1 outcome out of 6 other equal outcomes, or 5 other equal outcomes for 6 total. We should be more specific on that. So if I were to do this math to get the probability of both these happenings in sequence, I would just take probability of tails, that's 1/2, and I would multiply it by the probability of rolling a 4. That's 1 in 6. And now I just multiply through 1 times 1. That is 1. 2 times 6. That is 12, which a 1 in 12 chance of doing both of these consecutively. So just some quick compound probability. And again, if you wanted to say, now we could just tack on, we could say, well, what if I wanted 1 more tails? Well, we just multiply this by 1/2 to get 1 in 24, where you could tack on other outcomes in this sequence pretty easily just using that compound multiplication. So we're going to take a look at one more type of probability, which is essentially what happens if the probability becomes too hard to calculate. So let's say I wanted like a 3 dice roll, where it was like an orange dice, a blue dice, and a red dice, and I wanted to find the outcomes of that. And as we saw from the dice, it's not as simple as just saying there are 11 outcomes, 2 through 12, and we could kind of set each of them equal. There's kind of some combinations in this, and this was just for our 2 dice roll, so it's like if we didn't have our orange dice. But you can see where this was 36 different outcomes to track, and I also had to track like the 7s and the 6s combinations within it. This would get very complicated if I tried to add in another dice, because suddenly 6 times 6 becomes 6 times 6 times 6. And if I did like another dimension, it was like a 3-dimensional table, I would suddenly have 216 outcomes to track. I don't really want to do that. So there's got to be a better way. So what we're going to do is we're going to throw out our table and we're going to instead look at some simulation. So we're going to run our own little experiment and see if we can kind of get close to the probability or get as good as estimate as possible. So I'm going to bring a simulation for this. And before we start anything, we're going to play around with it a little bit. So we're going to start with something we know we're just one dice, where this will kind of track the frequency. So you can see I can roll it once. It's a 2. So it adds a marker for 2. And I could roll again. I could say, give me another roll. Well, roll the 2 again. Again, it rolled a 4. And we could do some simulations real quick on this. So we already know kind of what happens with the dice. We've rolled dice a lot and they're all equal sided. So we could say we really expect about the same number of rolls for 1, 2, and 3, and 4, and 5, and 6. They're all equally probable. So let's run a quick simulation. And I'm going to pause it really quick and actually here we go. So I have rolled the dice 25 times very quickly. And under this simulation, it says that a 1 is 9 times as likely as a 3. And we know that's not true. So maybe 25 rolls isn't enough. Let's try some more. We'll just let it simulate out for a bit. And as you can see, the more I roll, the more these bars start to level out. And if I were to quickly pause this and maybe say, let's tack on hundreds more rolls. Let's tack on just a couple 10,000. So now I'm suddenly at a little bit over 100,000 rolls. And you can see these start to even out a bit. Let's even tack on quicker. I'll see if I can very quickly, I'm going to switch over to mouse really quick. I'm going to very quickly see if I can tack on 1,000,000 rolls. And we'll see what happens. Million's a nice number we can just take it out of. So you can see now they're almost essentially the same. 166,000, 167,000. They've all kind of evened out. And if we go over to this, we can even convert into percentages really quick. These are decimals, so you can think of this as 16.6, 16.7%, 16.7%. They've all evened out with a ton of rolls. Even a million is a lot. They've all evened about to about the same probability. So we can essentially do the same thing with 2 dice. We'll reset and move over to frequency, where we can kind of get that pattern we saw, where if we tack on a lot, we see 7's the most probable, 6 and 8 a little bit less, and all kind of dwarf 2s and 12s, which are the rarest. But we want to investigate, of course, 3 dice. So we don't want to track 216 possible combinations. We just want to simulate it out. So what I'm going to do is I'm going to switch this over to 3 dice. And we're going to take a look at the combination. So I'll start just having it auto roll. And we see kind of it's spreading out. Maybe 12 is a little bit more probable. But we see under low amount of simulations, we can get a lot of variation. We want to tack on a lot. So let's quickly do a couple hundred more. We see a little bit more of a pattern. We're up to 1,130 simulated rolls. Let's tack on a bunch. See if I can quickly go out to maybe like 500,000 rolls. And you can see it looks like 10 and 11. We'll maybe just tack up to 1,000,000 really quick because it's not that long to do. And we can kind of see a pattern from this very quickly. We simulated it out. A 3, which you could theorize only rolling 1, then 1, then 1 would get you a 3. Very, very rare roll, where 10 and 11 must have a lot of combinations to get it to. So I'm going to copy this over real quick so we can work with it and calculate a probability. So I'll copy this back. There we go. Let's resize it because that is huge. So if I were to take this, let's say I wanted just a rough estimate for the probability, and let's put probability, and let's specify that it's experimental right here. So I'll put a little sub E. We'll say the probability of rolling a 10. See how likely that is. So we can do our total favorable outcomes. So we were able to roll a 10 124,811 times. Again, this is going to be quite the fraction in 1,130 rolls. And we could quickly do like a decimal approximation for this. Let's see. So 124,811. Convert it to a decimal really quick. 1 million. Let's do that one more time. I'm just going to do this with the mouse. 124,811. Divide that by 1,130. And we get about 0.12, and I'll round it off there. Which, that basically says our experimental probability for rolling a 10 is about 12.5%. And you could do the same thing here with the probability of rolling a 3. We'll just write that one out really quick. Probability of rolling a 3, that will be equal to 4,613 all over our total rolls. So 1,130. We'll quickly do that one real quick. So 4,613 divided by 1,130. And we get a much smaller decimal, which will mean a much smaller percentage. We'll round it off there. Which, if you were to do the math on this, use your percentage proportions, you would get 0.4%, or 4 out of 1,000 times. So we could do a quick probability calculation on a model that we didn't even know what the combinations were. Of course, we could have listed them all out and gone like, well, what's all the ways I could make a 3? What's all the ways of making a 4? But very quickly, we were just able to experiment this out. So again, make sure you bring any questions to your office hours. So hope to see you all on Wednesday, and I hope you have an excellent week. Take care.